You can say by the central limit theorem, I will approximate it by a normal distribution. All right, so let's do problem. Students is of course on random variable. With mean 100. And the professor in charge course has decided that if more than 120 students enroll, he will teach the course in 2 separate sections. Let me change to 120 or more. In 2 separate sections. Is less than 120 students. He will teach them all in the same section. What is the probability that he will have to teach 2 sections? Before we do this, let me mention the following. So we have a normal approximation to binomial, which is basically the central limit theorem. You also have a normal approximation to Poisson. And the idea is this. Again, from the beginning of the class, we know that if we have 2 independent Poisson random variables, you add them, they're again going to be Poisson, and their weights get added, right? So if x is Poisson n random variable, then what I can do is take x1, x2, xn to each be independent Poisson 1 random variables, okay, and independent. So it's important that they have to be independent. Then I know that the summation I equals 1 to n xi is going to be Poisson with 1 added up n times. X can be represented as the sum of independent identically distributed Poisson one random variables. So now I know that if X is a Poisson random variable with large parameter here, now this idea can be extended even when n is not an integer. The idea is if it's not an integer, this distribution is pretty close to the distribution where it is the closest integer, and then you can use the normal approximation. So if n is very large, that means this is just going to be a sum of IID, independent identically distributed random variables. I can use the central limit theorem here. It is x minus the mean. Expected value of x is going to be n. The variance of x is also n. Right? So minus the mean, that's n over square root of n, is approximately normal. That's what the central limit theorem says. Okay, so that's what we're going to use here. First, let's define a random variable. Let x be the number of students who enroll. Number of students that enroll in this class. And what do we know about x? We know that x is going to be distributed as Poisson. X has Poisson distribution with mean 100. And 100 is a pretty large number. What you're interested in calculating, you will have to teach two sections if x is greater than or equal to 120, right? Yeah, that is how the question is set up. So we basically define probability x greater than or equal to 120. If we use Poisson, what would it be? It would be the summation goes from 120 to infinity, probability that x equals k, right? And what is that? Summation k goes from 120 to infinity, e to the negative 100, 100 to the k over k factorial. So you don't want to calculate that.
Can you wait 1 second?
So if you don't want the precise answer, an approximate answer is good enough, you can use the central limit theorem, where you would use a normal approximation to the Poisson. So the central limit theorem basically shows that when you have Poisson with a large parameter, you can do this, and this would be approximately normal.
Is there a guideline to what parameter is large enough?
Well, any parameter where you don't want to do the calculation, it's fair enough for you to, you can just say that I'm going to use a Poisson approximation. I mean, clearly if n is 2, it might be more work to do a normal approximation.
Well, like 7.
I say work with when it's greater than 30. I say that's better. Yeah. Yeah. So I'm not going to give you guys a rule of thumb for this. Rather, how accurate you want the results. Take it to be n greater than or equal to 30. Clearly, if I ask you give me an approximate value of the probability, then chances are I'm asking you to use a normal approximation. Okay? And you can always ask me, should I use a normal approximation or not?
And then you'll say, I can't tell you that.
Well, since I haven't given you a rule of thumb here, I'll tell you.
Okay, thanks.
Clearly, if I say I want a numerical answer, you're going to have to use normal approximation because you're not going to be able to calculate that, right? Not sitting in class, yeah, so, yes, if the question says, I want the answer as a numerical answer, then I may not, if you ask me should I use a normal approximation, I may not answer that. Okay, so if I ask for a numerical answer, and you just leave your answer like that, you get points off because I asked for a numerical answer, and the only way you could get it was using a normal approximation.
Oh, I see what you're saying.
All right. Yeah, I think this exam, for everything, I'm going to expect a numerical answer. Because most of these things involve a normal distribution of calculating conditional probabilities. Yeah, you have to give a numerical answer for everything. All right. So using normal approximation. theorem, we do a normal approximation. So we have that that's lambda equals 100, right? So probability that x is greater than or equal to 120. Now there's something that I said earlier when we did normal approximation to binomial. Binomial was discrete, and we approximated binomial, which is continuous. So you have to do a continuity correction, right? Same thing here. Poisson is discrete. So if you're going to use a normal approximation, you're going to have to use a continuity correction. So if I'm including 120, then I need to go down by 0.5, or go down a little bit. Here's the continuity correction. Continuity correction. And then standard thing. From x, I'm going to subtract n times mu, or which is just your lambda here, which is 100, divided by square root of 100. Let's get to 119.5 minus 100, divided by square root of 100. Just using this result from here. And let's do this calculation. So at this stage, here we're using a central limit theorem or your normal approximation. You can say this approximately, and you can put in the standard normal random variable. And that you get 19.5 divided by 10. So you need to calculate by 1.95. And if you have your textbooks, you can look up your normal tables. 1.95 is. Oh, this was greater than or equal to, right? Or was it less than? So you calculate what that is, and
I'll use that technique on my exam.
so for Poisson distribution, again, if your mean is going to be very large, it's basically, you can think of your Poisson random variable as the sum of IID Poisson one random variables, so you can use the central limit theorem. So for binomial, where and when n is large, and when Poisson, when the parameter is large, you can just take the random variable minus the mean divided by standard deviation and use normal approximation for that. So this will always be approximately standard normally distributed. Another example where you don't have it as a binomial or you don't have a binomial or Poisson distribution, but your problem is set up as the sum of IID random variables. Find the approximate probability that the sum obtained between 30 and 40 inches. first let's set up this problem and then so it's the sum of what you get, which is the outcome of each die. Okay, so let xi denote the outcome of I die, and your I takes values 1, 2. And we are interested in the probability that summation I equals 1 to 10 xi is between 30, 40, including 30 and 40.
Questions?
Now you can see that the distribution of the sum is going to be pretty complicated. Like you've got to think of the joint distribution of x1, x2 to x10. They're independent, so not too complicated, but still, yes. If you had just a two-sided die, you just had coins, okay, it would have been simple. Heads or tails, and basically this would just be a binomial random variable. But a summation of xi's, each xi can take one of 6 values, right? So the distribution of summation xi is not trivial. So you're not going to want to spend time trying to figure out exactly what this probability is by exactly finding out what the, I actually like considering the different cases of how you would get summation xi to be between 30 and 40. So this is a case, even the n is 10, this problem is difficult enough that it makes sense to just use your normal approximation. Because now you see their IID, they're all dice, so they all have the same distribution, 1/6 probability of getting each of the outcomes, and 10 different ones are rolled, so they're independent. So we have the sum of independent, identically distributed random variables. We're in the setting where we can use the normal distribution, and it's difficult enough that we don't want to try and calculate this by hand rigorously. All right. Okay, so let's use, so for that, we're going to subtract off n mu and divide it by sigma square of n. So what's n? First of all, it's 10 in this case. What is mu? That's the expected value of xi. And your sigma square is your variance of xi. So let's first calculate mu and sigma square, and that's going to be easy because that's just for one, the outcomes of one die. So mu is, so it's, you can take the value 1 with probability 1/6, you can take the value 2 with probability 1/6, 3 with probability 1/6. Right. That's how you calculate the expected value for any one of the outcome of any one of the dice. So what's the average value of this? So 1, this is just
21 over 6.
Yeah, 21 over 6, 10, 15, 18, and 20, 21, yeah. 21 over 6, 3, 7, 8. So the average value of xi is 7 over 2, that's 3.5. Sigma square. For sigma square, let's calculate summation xi square first. Minus. So expected value of xi square. I don't have to put an xi, I can just write x1 because it's going to be the same for all of them. That's 1/6 times 1 square plus 2 square plus 3 square plus 4 square plus 5 square. So if someone has a calculator, can you tell me what answer you get? 25 plus 16.
55.
26,125, yeah. 6.
What happened to 6?
Again?
What happened to 6 squared?
Oh.
Uh,
Yeah,
91.
that just drop off.
Yeah, I think that's easy.
36.
81 or 91?
36
91.
and 91, right? Was 36?
91.
All right, thanks. So sigma squared is 91 over 6 minus mean square, so 49 over 4. 18. Okay, so what do you get this to be? 5, 7, 3. Is this right? 12. Okay, so let's just value 12. Question was probability that 30 summation I equals 1 to 10 xi is equal to 40. Now again here your xi's, they take only integer values, right? So the summation xi only takes integer values. So you're going to be approximating again a discrete random variable with a continuous distribution. So again it makes sense to use a continuity correction. If your xi's were measurements that were continuous, then you wouldn't have to use a continuity correction. But here, let's use a continuity correction. And we get that this should be probability that 29.5 is less than equal to summation 1 to 10 xi less than equal to 41.5. Minus 10 times 2 over square root of 10 times square root of 35 over 12. Minus 10 times 72 square root of 10 35 over 12. 5 minus 5
That's 10 times 7 over 2.
Yeah.
So 70 over 2. 35.
Yeah. All right. Alright, and at this stage you say it's approximately probability, write in whatever that value is, and now you can use this standard normal random variable and tell me what your values are. So again, in this exam, you have to use your standard normal tables when using the central limit theorem. So calculate that and tell me what you get those two values to be. That is this value
negative, there we go, at negative 0.0926.
Negative point zero
926.
926, okay, and here?
1.0184.
1.0184. Alright, so this is 1.0184 minus, this is basically what you tested on the second midterm, and this 0.0926. And this is at 1.0184 minus 5.0926.
We may want to double check. I'm seeing that we should have symmetry. If you just look at the numerators on both sides, we have a difference of 5.5 plus or minus.
What is 30 and 40 and then, oh
Yeah.
yeah, okay, and then we, yeah, that is a little strange, isn't it? Yeah, so which one is off? So that one says 5, yes, so this is 5.5 over, yes.
I'm sorry, I did that for the first one, negative 1.184. Does that
Okay,
sound
oh,
right?
oh, yeah, okay, then that,
If there's a
I'm
zero,
sorry.
right?
you mean 1.0184?
Yeah, I'm sorry, 1.0184.
Okay, all right, yeah, okay, yeah. Thanks for that, yeah. So you notice that it's just 10 off both sides.